In the last video, we just started to discuss, or we did discuss, the different states of matter. And one of the things about different states of matter, it really depends on a couple different types of bonding. And one of those types of bonding is called the intramolecular attractions. And this is actually the bonds that are within molecules themselves. And so what we're going to do is we're going to first look at the different bonds. And we've talked about this year. But the first one that we talk about is called covalent bonding. And covalent bonding, this is a perfectly covalent bond here. What's happening is we have two atoms of hydrogen, and those atoms of hydrogen, if you remember doing Lewis dot structures, each hydrogen happens to have one valence electron. And what they do is they create a bond between those two where they share this pair of electrons. And no one hydrogen gets them more often than the other. Now, there's other types of covalent bonds where we might take hydrogen or carbon and then bond a hydrogen to that. And so what's going to happen is now we have a combination of these two, and one of them actually has a greater attraction for electrons. Carbon's slightly more attracted, but for the most part, this is still a sharing of those two electrons and still a covalent bond. So the next one we're going to look at is ionic bonding, and we've talked about ionic bonding also. And as we look at this, what's going to happen in ionic bonding is instead of sharing electrons, we're going to take some electrons. And these bonds are created between metals and nonmetals. And so if you look at sodium, sodium has this electron structure, and these dots are representing the structure of the bond, or the electrons around sodium. And chlorine has its electron structure. Now chlorine's missing one electron from being perfect. And sodium really it's got this one electron kind of hanging out. And so as you see in the second picture here, well, this little electron is actually going to migrate itself over here and attach up. If you look in the second picture, you can see that little electron and where it moved to. Since electrons are negative, what's going to happen is that charge, when it moves over here, is going to be a -1. And when the sodium loses an electron, it's going to have more protons than electrons, and so what happens is it becomes a +1. What holds these two together is called an electrostatic attraction. It's kind of like two magnets sticking together. They're held together by this strong positive and negative force that draws them into one another. So that is our ionic bonding. A couple others that we haven't really discussed much. One of them is actually called a network covalent solid. And network covalent solids, the girls in the class really like network covalent solids. This particular network covalent solid is actually diamond. And what we're getting is we're getting lots of little bonds created between, here's a carbon, and that's bonding to a carbon, and that's bonding to a carbon. And what we get is this network of these individual little bonds. And what it does is it creates a very, very hard, very takes a lot of energy to break that apart and melt it. Okay, the one on this side is actually graphite, and what happens is in graphite's case, instead of being this really a three-dimensional structure, it kind of lays out in 2 dimensions as sheets. And what we get is we get these nice hexagonal shapes that are bound together, and then they kind of stack upon each other. And what you get is this layering. It's still very hard, but we can kind of shear off the different sheets as we start to play with it. Okay, so that would be network covalent. The next one we're going to look at is metallic. Now, metallic bonding is things that happen between atoms of, say, two silver atoms, two copper atoms. And what happens in metallic bonding is that the electrons are delocalized. And what that means is those electrons don't necessarily hang out with one atom or another, but they're actually passed very easily from atom to atom to atom. One of the benefits of this is that it conducts electricity. And so those electrons can be passed between basically a positive core of the atom, and these electrons hang out on the outside and are just kind of bounced back and forth between these positive cores. Another thing that allows metals to act the way they do is if we want to pound these flat, because those electrons will move, it allows this thing to be squished flat. It also allows it to be very, very ductile. In other words, being able to pull it out into a wire. Okay, those are all intra. molecular attractions. And the next one we're going to look at are intermolecular attractions. Now, intermolecular attractions are the attachments between two separate molecules. If I have a molecule of water and I have another molecule of water, what holds those together so they stay in liquid form or they stay in solid form? And that's what we're going to look at now. And the first one we're going to look at is actually called dipole-dipole. And if you think about this, what does dipole mean? Well, dipole means you have two poles. And the way that we determine if it's a dipole is we start to look at things like um, the electronegativities. And so if I have this compound, I'm going to expand it a little bit. We're going to just draw it out um, as a larger molecule here so we can draw on it. So if we have a hydrogen connected to a carbon, connected to a chlorine, connected to a chlorine, and connected to a chlorine. What happens inside this molecule is the electronegativity difference between hydrogen and carbon. Hydrogen has a slightly lower electronegativity. So what happens is the electrons that are in this bond move slightly in that direction. Now, the same thing here, carbon has a slightly less electronegativity than chlorine, so the electrons move out towards all the chlorines. So we have a net direction of electron flow towards the chlorines. And so you'll notice these arrows here are saying, well, the electron charge, or the dipole moment as it's called, is in that direction. And so what it's doing is the electrons are tending to hang out on this end, which makes this end of the molecule slightly negative. It makes this end of the molecule slightly positive. And those two little deltas, those are just giving us a partial charge. Now, because of that partial charge, these molecules actually hook together and hold together because of that charge. This end being slightly negative, well, this end slightly positive, they stick together, again, similar to magnets. So a dipole. First of all, we have to determine if the molecule is polar, and if the molecule is polar, then the type of intermolecular attraction will always be dipole-dipole. Now, there is an extreme case of a dipole-dipole, and it's actually called hydrogen bonding. And hydrogen bonding occurs when hydrogen is attached to a couple things: a hydrogen fluoride bond, a hydrogen oxygen bond, or a hydrogen nitrogen bond. So what happens here is, because of the electronegativity difference between hydrogen and oxygen, those electrons are moving in that direction, making this really pretty negative. Not enough to be an ion, but quite a bit. So this makes a very negative end. Well, this hydrogen is very positive. And so what we get is this little attraction between these that cause them to hold together. Now, if we have another water, same thing's going to happen over here. Here's our water molecule, and we get this little attraction that holds them together. And we're going to talk about properties that are affected by this holding together. Another molecule that would do this is ammonia. So ammonia has this structure that looks something like this. So the nitrogen is slightly negative and the hydrogens are all slightly positive. So if we draw another ammonia up here, put a hydrogen there, draw it up to a nitrogen, a hydrogen, another hydrogen, what we get is we get this attraction between those hydrogens and that nitrogen. And so those attractions hold these molecules together. And that helps us with some other properties that we're about to talk about after this. Now, what about things that are not polar? Well, these are called London dispersion forces. And these London dispersion forces, what happens is, if I put two molecules together that are similar without any kind of polar ability, what happens is the electrons tend to move in one direction. So, well, I drew the wrong direction since that's positive. The electrons will tend to move in that direction. What that does is it induces the other one to actually shift. So if this is an instantaneous dipole, this one becomes induced, so its electrons move that way. So this side for a moment is going to be slightly negative, and this side is going to be slightly positive. Now, it doesn't really like that, so what's going to happen is those electrons are going to head back that direction, and that's going to be the instantaneous dipole, which is going to cause this second one to also shift that way. And so now we have another induced dipole. Non-polar molecules don't stick together very well. Something like CH4. CH4 is non-polar. We have some polar bonds here, but the molecule itself is not polar. So if I have another CH4, they don't stick together very well because both of them are non-polar. And so this is one of the characteristics. Now, the longer the chain becomes of molecules, so if we make this chain a little longer, this is propane. Propane we can actually get into liquid form, but the problem is we need to really pressurize it. We kind of have to squeeze it together. And as we squeeze it together, it tends to stick and go into a liquid form. If we add one more carbon, it becomes butane. And butane we can put in a little plastic lighter. And then from butane uh, we go to pentane, which is a liquid at room temperature, but and tends to vaporize very rapidly. And so the longer the chain, kind of the stickier they get, but they're still two non-polar molecules trying to hold together. Okay, some of the characteristics that we actually observe. We're going to have to hold off for a second video on this, but right now, if you think about the things that we've covered intramolecular attractions and intermolecular attractions. And the thing that you need to pay attention to is the difference between those two. And so one of them is between the molecules. So if you have two separate molecules, what holds them together? That's called intermolecular attraction. If the bonds inside the molecule, those are intramolecular attractions. And so we'll come up with another video following up here on the effects of each one of those different types of bonding.